A universe of light and action, the cosmic dance. Have you ever looked up? Up at the night sky, stars twinkle light years away, sunlight warms your very face, light is all around us. It's a messenger, a painter, it carries energy, it reveals beauty. But what is this light, and how does it interact with stuff? Matter is the other player, everything you can touch, yourself, your dog, this planet, distant galaxies far, far away. All of it is matter, made of tiny, tiny parts. These parts are called particles. They are the building blocks. They make up everything we see. Light and matter are not separate. They are in a constant dance, a cosmic ballet, if you will. Light pushes matter. Matter can create light. This interaction is fundamental. It shapes the entire universe, from the smallest scales imaginable to the grandest cosmic structures. This dance isn't just simple. It's not like a ball bouncing. Down at the very smallest level, the quantum level we call it, things get wonderfully strange. Old rules seem to break, new rules take over instead. Welcome to a new kind of reality, a reality we will explore. So how do we describe this dance of light and matter? Science has a special theory, it's called Quantum Electrodynamics, or QED for much shorter. It's a cornerstone of physics. One of our best achievements, it tells a deep story about how things truly work. QED is part of something bigger, a framework called quantum field theory. Imagine fields filling all space. One field for electrons perhaps, another field for light itself. Particles are just tiny ripples, vibrations in these cosmic fields. QED focuses on two main things: light and electrically charged particles. Light is made of particles. These particles are called photons. They have no mass, no charge. They always travel at light speed, the ultimate cosmic speed limit. Charged particles are things like electrons. Electrons are in every atom. They carry a negative charge. They are essential for matter. QED is incredibly powerful. It makes predictions about interactions, how a photon affects an electron, how two electrons might push apart. These predictions are amazingly accurate, to many, many decimal places. It's one of science's great triumphs, showing we can understand nature even at its most hidden levels. Now things get a bit peculiar. Think about these tiny particles, electrons, photons, and the like. Are they like tiny billiard balls, solid bits of something definite, or are they more like waves, spreading out like ripples on water? The quantum answer is surprising. They are somehow like both. This is called wave-particle duality. A mind-bending concept it is. Sometimes light acts like a wave. It bends around corners, for instance. Sometimes it acts like a particle, hitting a surface, one photon at a time. The same is true for electrons. They can be waves, they can be particles, it depends on how you look. Because of this wave nature, particles don't have exact paths. Not like a thrown baseball, no. We can't know precisely where it is, and precisely where it's going. There's always some fuzziness involved. A fundamental limit to our knowledge. This is called Heisenberg's uncertainty principle. It's a core idea in quantum physics. So, how do particles move then, if not on definite paths? They move according to probabilities. There's a chance of finding it here. There's a chance of finding it there. QED calculates these probabilities. The chance of an interaction happening, the chance of a particle going left, or the chance of it going right. How do particles actually interact? How does one electron feel another? If they are not touching directly, they use messengers of a sort. These are called virtual particles. They are a key part of QED. They carry forces between particles, like tiny, fleeting postmen, delivering messages of push or pull. Virtual particles are quite strange. They are not like normal particles. We cannot detect them directly. They pop into existence briefly, then they vanish back into nothingness. They borrow energy from the vacuum for a very, very short time, allowed by that uncertainty principle. Energy can be uncertain for a moment. Think of the electromagnetic force, the force that makes magnets stick, or makes like charges repel. In QED, this force is carried by virtual photons specifically. An electron wants to push another, it sends out a virtual photon. The other electron absorbs it and recoils, feeling the force. These virtual particles are everywhere, mediating all the fundamental forces, not just electromagnetism, mind you. Other forces have their messengers too. They are essential for reality. Without them, particles wouldn't interact. Atoms wouldn't hold together properly. The universe would be very different, a much less interesting place indeed. Section 5. Feynman's doodles drawing how the universe works. Calculating these quantum interactions with all those probabilities and all those virtual particles can get incredibly complicated. The mathematics can be terrifying. Long equations fill blackboards. It was a major challenge for physicists in the early days until a genius came along. His name was Richard Feynman, a brilliant, quirky physicist. He had a revolutionary idea. What if we could draw the interactions? Turn complex equations into pictures, simple diagrams to show what happens. These are now called Feynman diagrams. They transformed how physics is done, making the complex much simpler. What do these diagrams show? They show particles moving through space-time. Straight lines often represent matter particles, like electrons, for example, or their antimatter cousins, positrons. Wavy lines usually represent force particles. For QED, that means photons. These are the messengers we talked about, the virtual photons carrying forces. Where these lines meet, it's important. These meeting points are called vertices. A vertex shows an interaction. An electron might emit a photon, or an electron might absorb one. Each line, each vertex means something. It corresponds to a mathematical term, a piece of that complex calculation. The diagrams guide the maths. Section 6. An electron's tail, a simple Feynman diagram. Let's look at a simple example. Imagine two electrons approaching. They both have negative charge, so they should repel each other, like pushing two magnets together. How does QED show this happening? We can draw a Feynman diagram. It tells the story quite clearly, a story of a virtual exchange. First, draw two straight lines. These are our two electrons, moving towards each other perhaps. Time usually flows from bottom to top or sometimes from left to right, so one electron comes in, the other electron also comes in. They are minding their own business until something happens between them. Suddenly, one electron does something. It emits a virtual photon. On the diagram, a wavy line. This wavy line connects to the electron's line at a vertex, an interaction point. The electron changes its path slightly. It recoiled from emitting that photon. The virtual photon now travels across the space to the other electron. The second electron then feels it. It absorbs this virtual photon. Another vertex on the diagram appears where the wavy line meets the second electron. This absorption gives it a kick. The second electron changes its path. It moves away from the first. The two electrons have repelled, all thanks to that virtual photon. Section 7. QED in our world. From theory to technology. These diagrams and QED itself are not just pretty pictures or abstract thoughts for theorists. They are incredibly useful tools. They help us understand the universe with breathtaking precision too. QED's predictions have been tested again and again for many decades, and they match experiments perfectly. One famous example is subtle, the magnetic strength of an electron, called its magnetic moment technically. QED predicts this value very precisely, to about 1 part in a trillion. Experiments have measured this value and the numbers match beautifully. This tells us QED is right, or at least extremely close to it. This deep understanding has power. It fuels technological progress. Many things we use every day depend on our knowledge of QED. Lasers, for example, are one. They rely on how light interacts with atoms, specifically electrons. Medical imaging, like MRI scanners, also uses principles from QED. Even the computer you might use, or the smartphone in your pocket, the transistors inside them work because we understand electrons and how they behave in materials. Particle accelerators, great machines that smash particles together, they use QED to predict outcomes and to design experiments carefully. Section 8. The enduring light of QED understanding our reality. So, quantum electrodynamics is vital. It's more than just a theory. It's our best description yet of how light and matter chat at the very smallest, deepest level. It has opened a window into the fundamental workings of reality, showing us an amazing quantum world full of probabilities and virtual exchanges. Richard Feynman's diagrams helped. They gave us a language, a way to visualize the invisible, to tame the mathematical beast, and to calculate what happens when particles meet and greet, or when they decide to repel. Science moved forward greatly thanks to these simple-looking drawings. The impact of QED is huge. It changed physics forever, truly. It showed us that the vacuum, the emptiness of space, is not empty. It's a bubbling sea of potential, virtual particles popping in and out constantly everywhere all the time. This transformed our cosmic perspective, our place in this grand universe. From understanding starlight so far to designing the tiny microchip, QED's principles are at play. It's a testament to human curiosity, our relentless drive to ask why, and to seek out the answers. The universe is a complex place, but with tools like QED we can begin to comprehend its beauty and its intricate, amazing rules.